So thank you.
I think you have to turn off that one. Yeah, try now.
Now? Good. Who's testing your turn? You clearly tested mine. I'm supposed to. So thank you, Helen, for the invitation. I'm very excited to be here. So as she said, I'm a philosopher of science. I'm an associate professor in Salzburg. And as a philosopher of science, I'm very fascinated by black holes. So for many years, I was doing research on the Transplanckian problem. I worked with some colleagues on that issue, and I actually presented the results of that research, I think in 2019 here in the Black Hole Initiative conference. But a few years ago, I got interested on the role of thought experiments in black hole physics, and in particular in black hole thermodynamics. And this is what I am going to talk about today. So I know that, okay, sorry, it's not much. I know that I don't need to explain to you what black hole thermodynamics is, but let me start from the beginning. So we know that black hole thermodynamics is a discipline that ascribes thermal properties to black holes. According to black hole thermodynamics, black holes have temperature, they have entropy, and other thermal properties. So importantly, although there has been important outstanding research on trying to test the existence of black holes, especially due to all the achievements of the Event Horizon Telescope, none of these, and correct me if you think differently, but none of these should be taken as empirical evidence for black hole thermodynamics. So the prediction of black hole thermodynamics in particular are very hard to test, at least directly. And one of the reasons is because the temperature, for example, is so low that it's almost undetectable from Earth. So there's no even hope that in the medium or long term, we will have direct empirical evidence for black hole thermodynamics. So in this scenario, the use of what we call theoretical and non-empirical tools like thought experiments and mathematical derivations is extremely important. And in particular, thought experiments are essential in the investigation of black hole thermodynamics.
Do we have evidence that the area of the horizon always increases? Like if you have one of these binary mergers or whatever, and you calculate the area of the independent black holes, it's not evidence for like Hawking radiation, but it's a evidence for the area being non-decreasing. Maybe anyone? I would have thought that they found, but
not even this.
That was one of the claims, right? Okay.
Yeah.
So it's not thermal, but it's areas not increasing.
Yes, we are far from having at least direct empirical evidence, and in particular for the predictions of black hole thermodynamics, like temperature, etc. So in this scenario, the use of thought experiments is extremely important, is central in the research of black hole thermodynamics. For instance, Eric Curiel, that I am sure you know very well, says, why assume a black hole has an entropy in the first place? The best answer to this is implicit in a series of thought experiments. And also Chris Wuttrich, another philosopher of physics, says Gedanken experiments concerning the limits of the amount of thermodynamic work that can and cannot be extracted from black holes lend some support to the idea that black holes are thermodynamic in nature. So you see how much this research is relying on thought experiments. And this is a conversation that I had with Juan Maldacena that I'm sure you know also very well. So we had a meeting, a Seven Pines meeting a few years ago, and he was presenting his latest research on two meanings of entropy, two definitions of entropy. And I asked him, how much do these results rely on thought experiments? And he answered me 100%. After that, he thought a little bit more about it. And he said, well, maybe not 100%, but 97% of what I said rely on thought experiments. So I found all of this very puzzling from a philosophical point of view, because as you know, thought experiments are not real experiments, so they are not performed in a real laboratory, they are performed in the laboratory of the mind. So how can it be that by using our imagination, we can learn something about the world, and in particular about black holes? So the first question that I asked was, should we take thought experiments in black hole thermodynamics seriously? And the second, if we have to take them seriously, what exactly can we learn and what can we not learn from thought experiments in black hole physics? So these were the leading questions of this research. And what I'm trying to do today is to give you an answer to these two questions. So when I started doing this research, there was a colleague of mine working in Salzburg on the philosophy of thought experiments, Rawat El-Skaf. So we started working together on this. And during this research, we realized that philosophers of science who were working on the epistemology of thought experiments were only considering historical cases in physics, so they were not taking into account contemporary physics. And on the other hand, philosophers of physics who were working on black hole thermodynamics were mainly based or focused on the role of mathematical derivations and the role of analog experiments in black hole thermodynamics. And they were not really studying systematically the role of thought experiments here. So one of our motivations was to fill this gap in the literature and start a research on a systematic research on the role of thought experiments, specifically in black hole thermodynamics. So we analyzed different thought experiments. As you know, there are plenty of thought experiments in black hole thermodynamics, but we decided to focus on just the two thought experiments that gave birth to black hole thermodynamics. That is Wheeler's demon and Gero's thought experiment. And the reason why we took these thought experiments is because they are simple enough to let us understand the epistemology of thought experiments here, and also the limits of thought experiments in black hole thermodynamics. So I will now explain you these thought experiments in case you don't remember them. So the first thought experiment is Wheeler's demon or Wheeler's thought experiment. In 1970, Bekenstein was doing his PhD in Princeton, and Wheeler came to visit Princeton and asked him the following question. So what would happen if we throw 2 cups of tea into a black hole? So this is a very simple thought experiment. And 2 years later, Bekenstein came up with an answer in his celebrated paper, one of the papers that gave birth to black hole thermodynamics, that was black holes and the second law. So here he said that if we apply the second law of thermodynamics to this scenario proposed by Wheeler, and a theorem of general relativity, that is the no-here theorem, that tells us that a black hole is uniquely determined only by the mass, the spin, and the electric charge, we will arrive at the conclusion that we cannot exclude the possibility that the entropy would decrease, the overall entropy would decrease in the process when we threw 2 cups of tea into a black hole. And the reason is that when we threw 2 cups of tea into a black hole, we know that the entropy in the exterior of the black hole will decrease. And because of the no-here theorem, we cannot be sure that the entropy in the interior of the black hole would increase. So the no-here theorem doesn't tell us anything about entropy. So again, we cannot exclude in this scenario the possibility that the second law would be violated. So he saw this as a possibility that the second law would be transcended, in the sense that it would lose its predictive power. But in the same paper, he tried to solve this tension between the second law and the no-here theorem, suggesting, and what you probably are familiar with, that black holes have entropy indeed. But they don't have common entropy, they have an entropy that is proportional to the surface area of the black hole. And the motivation to associate black hole entropy with the surface area was Hawking's theorem that the area of the black hole should never decrease. So he saw the analogy between entropy never decreasing with area not decreasing, and he came up with this definition. And with this definition, he formulated a revision of the second law of thermodynamics, or a modification of the second law of thermodynamics that is now known as the generalized second law. that tells us that the entropy of the black hole plus the entropy, the common entropy, should never decrease. And this is how he tried to solve this apparent tension or contradiction between the no-here theorem and the second law that was exposed by Wheeler's thought experiment. So now, before we analyze more philosophically what is the role of this thought experiment, I will explain the second thought experiment that I want to analyze. And this is Geror's thought experiment. So also in Princeton, Geror went, when Bekenstein was studying there, Geror came to visit Princeton and gave a talk in which he suggested the following thought experiment. Imagine that we have a box. It doesn't need to be a red box, but imagine that we have a box in the vicinity of a black hole, and that we have a pulley that allow us to lower the box infinitesimally slow towards the horizon. We can show by applying the laws of thermodynamics and the laws of general relativity here that if at the horizon we let radiation to escape, as radiation escapes, we will be able to pull up the box. And if we let all radiation to escape, we will be able to pull up the box to the origin. So that means that in this case, we will be able to turn all the heat that was used to lower, or all the energy that was used to lower the box into work. So this, of course, implies a violation of the second law of thermodynamics that was realized by Bekenstein. And not only that, so Bekenstein realized that in this situation, we would not only have a violation of the second law of thermodynamics, but we would have a violation of the generalized second law. And the reason is that in this situation, the efficiency of the machine would be 1. And if the efficiency of the machine is 1, we can show that the temperature of the black hole would be 0, which also implies that the entropy of the black hole would be 0. If the entropy of the black hole would be 0, we would have a decrease of the entropy in the exterior of the black hole, because we would let radiation to escape without necessarily having an increase in the entropy in the interior of the black hole. So Bekenstein realized that this thought experiment shows an inconsistency or a problem, not only for the second law, but also for his generalized second law. So in contrast to Wheeler's thought experiment, he didn't came up with a resolution of this thought experiment in the paper of 1972. And the first resolution or serious resolution to this thought experiment came in 1981 when he suggested a physical bound. So he realized that most of the problems here appear when the box reaches the horizon. So he suggested, he calculated the maximum distance at which we could lower the box without violating the generalized second law. And by doing that, he calculated the maximum distance and he imposed a physical bound. So he assumed that the box could not be lowered beyond that distance that is just enough to prevent a violation of the second law. And that is what is now known as Bekenstein bound. So there are many Bekenstein bounds, but the first one, or the most important one, was this that says that the entropy over the energy should be always minor or equal than 2p air, where air is the radius of the body. So 1 year later, Unruh and Wald published a paper in which they argue against Bekenstein resolution. First of all, because they showed that the Bekenstein resolution wasn't robust enough. So they showed that if we consider, for example, a rectangular box instead of a cubic box, the physical bound would not prevent a violation of the second law. And second of all, they were unhappy with Bekenstein resolution because they found it ad hoc. And to my understanding, it also seems a little bit ad hoc. So they assumed that there should be a way of solving this problem or this inconsistency between the generalized second law and the laws of GR by postulating a physical mechanism that prevents the box from reaching the horizon. So he said it's not enough to just put a physical bound by hand. We should think about a physical mechanism that prevents the box from reaching the horizon. So they built an analogy between what happens in the vicinity of the horizon with what happens when bodies are embedded in liquids. So what happens there is a buoyancy force that pushes up the body up. So they assume that in the vicinity of the black hole, there should be also something like the buoyancy force that prevents the box from reaching the horizon. And they thought that this buoyancy force would be associated to the quantum effects that are caused by Hawking radiation. So here is also when Hawking radiation came into scene. So it's Hawking radiation that creates this thermal atmosphere that causes a buoyancy force that becomes infinitely large near the horizon and therefore prevents that the box reaches the horizon. So it prevents also that the generalized second law is violated in the scenario, in the case of Gero's thought experiment. Although this resolution was a little bit more convincing because it postulated a physical mechanism, Bekenstein was very unhappy with this resolution by Unruh and Wald, because he also saw that it wasn't valid in all situations, so the resolution wasn't robust enough. If we consider different circumstances, we would show that the buoyancy force is not sufficient to prevent a violation of the second law. And then he suggests another physical bound, and this discussion continued until sadly, well, Bekenstein died. So they never actually reached a consensus on how to solve the
What was
Gero's
the example Bekenstein showed, which Unruh and Wald does not take care of? Because it looks like this argument works.
Many different examples. So I don't remember any in particular now, but many different examples he showed.
It's published in papers.
Yeah.
Take
All
a
of this is published. Yeah. So it is.
Because
But
Unruh
it
Wald
wasn't,
is
it wasn't only one. There
Okay.
were different examples in which he showed. So he found the physical mechanism a little bit convincing, but it wasn't enough to prevent it under all circumstances. So he started testing with robustness tests, sort of this buoyancy force, and he saw that if you change some of the conditions, then it would not be enough to prevent the physical bound. So you would not have a distance that is enough to prevent the physical bound, to prevent the violation of the generalized second law. So they never reach a consensus here. They continue back and forth with the series of papers, and the discussion remains open until now, like how to solve Gero's thought.
You say until now, you mean it is unresolved, or those 2020 papers have a new proposal?
They have new proposals. Some of them had to do with Maldacena's duality as well. So they have been really new proposals, but to my understanding, there's still no consensus. In contrast to the resolution of Wheeler's thought experiment, in which almost all the community accepts his resolution that is attributing entropy to a black hole. In this case, in the case of Gero's thought experiment, there is no widely accepted resolution. So there are alternative resolutions on how to solve this problem, but no one resolution that is widely accepted. No consensus, at least on this issue. So, but what we have seen about these thought experiments that are very simple is enough to try to understand what is the epistemic role of thought experiments in black hole physics, which means what can we learn and how can we learn from thought experiments in black hole physics. But to answer these questions, I think it's useful to go a little bit to the philosophical literature and to review the proposals that philosophers have done with respect to the epistemic roles of thought experiments. So in the philosophy of science literature, there are different views on why can we learn something about with a thought experiment. Thought experiments have puzzled philosophers for a long time, but as I said, the discussion has been mainly focused on historical cases like Galileo's thought experiments and Einstein's thought experiments in particular. And in this discussion, there are different accounts. One account is the arguments approach by Norton. He said that we can learn from thought experiments because thought experiments can always be reconstructed as arguments. So what we do with a thought experiment is just to organize our thoughts. This is why it's not mysterious that we can learn something from a thought experiment, because we learn from a thought experiment in the same way we learn from arguments, from deductive and inductive arguments. There is another account of thought experiment that is less popular, that is the Platonic intuition-based account by Brown. So Brown believes that we can learn from thought experiments something a priori about the laws of nature. This is the less popular account because philosophers of science tend not to be Platonic. So this sounds extreme for many philosophers of science. There is another account that is the mental models account that contradicts Norton's account that says that thought experiments cannot always be reconstructed as arguments. Thought experiments are mental models. They are models in the mind that represent in an approximate way a realistic situation. This is the reason why we can learn something about thought experiment. There is the non-empirical virtues account by Bokulich that says that we don't learn something directly about the world by using a thought experiment, but we learn about virtues of our physical theories, for example, about the consistency of our physical theories, about the simplicity of physical theories, etc. And there is another account that we reviewed that is the understanding account by Stewart that says that thought experiments don't give us knowledge, but they give us understanding. They have a pedagogical role. But there's a recent account suggested by my co-author, so you assume that correctly that we endorse this account, but I will explain you why. It's not just because he was my co-author. I can show that this is the account that best fits with thought experiments in black hole physics. And this account says that the principal functions of thought experiments are to reveal and resolve inconsistencies. So we can learn something about thought experiments because they help us reveal inconsistencies that were well hidden in our physical theories. And they can also help us resolve or give us ideas to resolve these inconsistencies. So we reach these principal functions by following different steps. First, scientists target a theoretical question, probably. Then they build a scenario, a contrafactual scenario that involves different idealizations and abstractions, as in the two situations that we examined. Then they unfold a scenario, which means that they apply theoretical statements to this scenario, like the laws of thermodynamics, for example, the laws of general relativity. Then by applying these theoretical statements to the scenario, they obtain a result that is the output of the thought experiment. And then normally they interpret this result as revealing an inconsistency between physical theories, and finally they try to solve this inconsistency. So in this paper, we try to show that the thought experiments that we examined in black hole thermodynamics fit perfectly well this account. And we went beyond this account by stressing that the character of the revelation of an inconsistency is very different from the character of the resolution of the inconsistency. Whereas the revelation of an inconsistency is conclusive knowledge. I know this is a strong claim, but we are very committed to it. We can conclusively learn that there is an inconsistency or a tension between different theories by performing a thought experiment. The way of solving the inconsistency is just conjectural. And you can see that when you review the literature, maybe when you review your own work. So now let me reinterpret the thought experiments that I already explained to you by having this theory of thought experiments in mind. So if we think about Wheeler's thought experiment, that was the idea of throwing 2 cups of tea into a black hole, then we see that it fits perfectly this account. So the main role of this thought experiment is precisely to show us that there is a tension between the no-here theorem of GR and the second law of thermodynamics. So more in detail, Wheeler wanted probably to test the compatibility between thermodynamics and general relativity in the context of black holes. And this is why he postulated this contrafactual situation in which we throw 2 cups of tea into a black hole. So he built a particular scenario that includes several idealizations, including the stationarity of the black hole, which turns out to be very important in black hole thermodynamics, as you know. And then he unfolded the scenario as well as Bekenstein did. So they applied theoretical statements like the black hole, the second law of thermodynamics, and the no-here theorem into this situation. And by doing that, they obtained a result. And the result was that the entropy of the universe might have decreased in this process because the no-here theorem doesn't tell us anything about entropy. And then in step 5, they interpret this result as a revelation of an inconsistency or a tension between the second law of thermodynamics and the no-here theorem. And then what Bekenstein did was try to resolve this tension by postulating that black holes have entropy and also by generalizing the second law so as to prevent a violation of the second law. So I believe, and as I said, I am committed to this, so if you want to discuss it, I'm happy to. I believe that the revelation of an inconsistency should be interpreted as conclusive knowledge, which means performing a real experiment would not necessarily give us more information about this or more evidence of this. And the reason is that this thought experiment, even if it happens in the laboratory of the mind, is just enough to unify the domain of two theories that are normally used to describe different domains. So what we do with this contrafactual situation in which we throw 2 cups of tea into a black hole is to unify the domain of thermodynamics and general relativity. And this is why this is enough to see this tension between the theories conclusively. So we consider this as we interpret this as an external inconsistency because at first sight, there is nothing that tells us that the no-here theorem is contradictory with the second law. We can reveal this contradiction just by applying these statements into a particular scenario, that is the thought experiment. On the other hand, the way of solving this inconsistency is only conjectural, it's only speculative. In fact, as I said, there is consensus now that Bekenstein resolution is the best resolution of Wheeler thought experiment, that we should attribute entropy to a black hole and that the second law needs to be generalized. But this was just a possible resolution. In fact, when he published the paper in 1972, not everyone was convinced about this resolution. Everyone was convinced about the problem between the second law and the no-here theorem, but not everyone accepted his resolution that black holes had entropy. In fact, Wald himself, that works on black hole thermodynamics, wasn't convinced about that. He said, however, at the time, I felt that this was an utterly ridiculous project to work on. First, as already mentioned, I was not troubled by the apparent transcendence of the second law of thermodynamics because it was a statistical law anyways. Second, the analogy between the second law and the area theorem seemed extremely artificial because we are marrying, he would say, a statistical law with a mathematical theorem. So he wasn't, as many physicists, he wasn't convinced by Bekenstein resolution, but he was convinced by this tension between the second law and the no-here theorem. I will tell you later what convinced Wald actually to endorse that black hole, the idea that black holes have entropy. But now let us move on to the second thought experiment. Again, we can see that it fits perfectly this account. So Gerosh probably wanted to test the compatibility between thermodynamics and general relativity in the context of black holes. And this is the reason why he suggested this thought experiment. Then he considered a contrafactual scenario, that is the box near the black hole that is lowered by a pulley. And he applied several theoretical statements to this scenario, in particular the laws of general relativity in the horizon and the laws of thermodynamics. And he obtained a result and concluded that in this particular scenario, all the heat could be converted into work. And then he interpreted this result as a possible violation of the second law of thermodynamics. So he interpreted this result as a contradiction of the laws of general relativity, especially when they are applied to the horizon of the black hole with the second law of thermodynamics. And then Bekenstein stressed that this result not only may imply or can be interpreted as a violation of the second law of thermodynamics, but also of the generalized second law of thermodynamics. And then what they tried to do was to solve this inconsistency. So Bekenstein suggested that there was a physical bound, then Unruh and Wald suggested that there was a physical mechanism, like the buoyancy force that prevents the box from reaching the horizon, and other resolutions have been suggested here. So then you can see here, especially here, the conjectural character of this resolution part. Again, I think that we can conclusively learn from this thought experiment that there is a tension between the laws of thermodynamics, general relativity, and also quantum mechanics, because it comes into scene here. And we can learn this conclusively because this thought experiment, even if it happens in the laboratory of the mind, is enough to show us, to unify the domain and show us the tension of these statements. But what we can also try to speculate how to solve this inconsistency. But as I said, this only has a conjectural character. So that there is a physical bound was a conjecture, that there was a buoyancy force was also a conjecture, and there were just different possible alternative resolutions to this tension that was revealed by the thought experiment. Page, for example, when thinks about the physical bound by Bekenstein said, perhaps the main difficulty is how to give precise definitions for the system and for its S, E, and R. For various choices of these definitions, one could easily come up with contra-examples to the conjecture. Yeah. So what we also believe is that the information loss paradox, which is a very famous and important thought experiment, can also be interpreted in this way. We said a little bit about this in the paper, but now we are doing a more systematic research on different resolutions. We haven't complete this research yet, so I'm not going to tell you more about this, but we have the intuition that is justified. I think that our account also fits very well with the information loss paradox. So at least some physicists seem to agree with us that the main role of thought experiments is to reveal contradictions. For example, Susskind in the popular book, The Black Hole War, says, theoretical physicists are struggling to gain a foothold in a strange land. As in the past, thought experiments have brought to light paradoxes and conflicts between physical principles. This book, that is this popular book that I mentioned, is about an intellectual battle over a single thought experiment, that is the black hole paradox. And more importantly, maybe, Polchinski, who was one of also the inspirations for this work, he gave a talk in 2013 in which he was defending the idea that thought experiments in black hole physics, as many other thought experiments, have the main function of revealing problems between statements. He said, the theories of quantum mechanics and general relativity are each very well tested and successful in their own regimes. Thought experiments can expose inconsistencies. Black holes have proven to be useful arenas for the confrontation of black holes, for the confrontation of quantum mechanics and general relativity. So now, just to finish, you might wonder. I said that the revelation of an inconsistency should be interpreted as conclusive knowledge, but the resolution is only conjectural. So you might wonder, what can we do to favor one resolution instead of others? And the answer that we would give is that ideally you would like to have direct empirical confirmation to know how to resolve an inconsistency. But again, in the case of black hole thermodynamics, that's very far away, if we're optimistic, maybe. So what can we do when empirical evidence is entirely lacking? I think we shouldn't be hopeless here, and we should think about alternative methods to favor one resolution instead of others. And I will not talk about confirmation because that's very complicated. It's a very big word in philosophy, but I will talk about at least some evidence supporting a resolution instead of others. So the first tool that we might want to use to complement the results of thought experiments are robustness tests. As you have seen already from what I have said, or from your own research, robustness tests seem to play a very important role here. So actually, Walt and Unruh attacked Bekenstein resolution because they showed that the resolution wasn't robust enough. So they made tests to test the robustness of Bekenstein resolution. And also Bekenstein criticized Walt and Unruh's resolution by showing that their resolution wasn't robust enough, so that not in all situations help us prevent a violation of the generalized second law. So robustness tests can help us here to see which resolutions are better than others. If a resolution is not robust enough, maybe it's not a very good resolution. Another tool that we could use in this case, in which we don't have evidence, are mathematical derivations. So now David Wallace, that I'm sure you know, philosopher of physics, and also many physicists, including Bell Giorno working here, believe that mathematical derivations can play also a crucial role in making us believe in the predictions, in increasing our belief on the predictions of black hole thermodynamics, and also in favoring some resolutions of the paradoxes that are exposed by thought experiments. Especially if the mathematical derivations are robust enough, we have more reason to trust them. That is what David Wallace said, for example. The reason why people believe on black hole temperature is that under different assumptions or working with different assumptions, we can get to the same result. And this is actually what Wald himself said that convinced him of black hole thermodynamics in general. He said that he wasn't convinced when Bekenstein presented these thought experiments, and he published his paper in 1971, but he was convinced in 1974 when Hawking derived the black hole temperature. So he said, using his words, he said, then a miracle occurred. In 1974, Hawking calculated particle creation effects for a body that collapses to a black hole. And he made the amazing discovery that a distant observer will see a steady thermal distribution of particles emerge at the temperature K over 2P. So it was the mathematical derivation that actually convinced him, not the thought experiment.
Do you think there's a sharp line between thought experiments? Maybe we'll get to this in mathematical derivations.
Yes,
because
it's
every
very-
calculation inquires about
Yes,
some setup,
yeah.
some assumptions that are
Absolutely.
made. I mean, is the line even so sharp?
Absolutely, absolutely. Sorry, I don't think it's very sharp. I think you're absolutely right to think that it's not very sharp. But I'm thinking here about additional support for the thought experiment. According to the thought experiment, when you build it, sometimes you do perform some mathematical derivations. For performing the mathematical derivation, you need to think about the thought experiment first. But if you try to separate them, then you can try to consider mathematical derivations as extra support for empirical support, or not empirical support, evidential support for a resolution of the thought experiment. So, and the third tool that's still more contingent is the use of analog experiments. So there is a very important and heated discussion in philosophy of science as to whether analog experiments can give us confirmation. You probably all know what analog experiments are, but in case you don't, what I have in mind here is when you perform an experiment not in the target system, but in a source analogous system. So instead of performing the experiment in the black hole, you perform an experiment in a condensed matter system, for example. So as I said, in philosophy of science, there is a very important heated discussion as to whether these analog experiments can give us confirmation. I will not commit here to anything in particular, but I will say that if we agree that analog experiments can provide at least some empirical support for the predictions of black hole thermodynamics, then you might also agree that they can provide support for one resolution instead of the other. So this is the claim that we make. And this is the claim that I am committed to at the moment. So in fact, this has seemed to have played a role in Wald and Unruh resolution of Gero's thought experiment. In fact, what seemed to have motivated the idea of the buoyancy force was an analogy with what would have occurred in the vicinity of the Unruh radiation. So Page said, for example, Wald and Unruh independently rediscovered this mechanism that was the buoyancy force after realizing that the Unruh radiation would make the buoyancy effect real, right? So it seems that analog experiments could maybe play a role also in favoring one resolution instead of others.
But that's an analog thought experiment.
That's an analog thought experiment. That's true. That's true. But since it is possible to do analog experiments and test Unruh radiation, you might think that if you can test Unruh radiation and you believe on that analogy, you might also favor one resolution instead of the other. Good. So now let me conclude. So what I am mostly committed to is that the principal functions of thought experiments in black hole thermodynamics, and I would say not only of the experiments that I reviewed here, but also other thought experiments in black hole thermodynamics, is to reveal and resolve inconsistencies. So those are the main epistemic functions of these thought experiments. And I also stress that where the revelation of an inconsistency provides or should be interpreted as conclusive knowledge, because it helps us unifying the domain of theories that normally describe different domains. The resolution is only conjectural, and when you go and review this discussion, you can see the conjectural character of this resolution part. And before thanks, and this is more general. What I have also tried to convey, but you probably know this already, is that black holes are an ideal arena to understand the importance of non-empirical tools in the absence of direct empirical evidence. So this is also one of the reasons why we as philosophers of physics are so fascinated by black holes. Thank you.
Okay, thanks. Questions? Yeah.
Many thought experiments that you described, maybe all of them, had a visual representational aspect. Something you could picture, dropping, lowering this box, or. But is that a necessary or accidental part of the thought experiment? I mean, you could think, for instance, and I'm a little bit responding to the question about the relationship of thought experiments to mathematical arguments. If you have an argument that's an argument by reductio, kind of, if you believe that, then you get a perpetual motion machine. Or if you do that, I mean, something that leads to the contradiction with itself or something else that we hold dear. You could imagine, there are many such arguments in physics that aren't intrinsically visualizable. If you could accelerate infinite, if you did this, you would be supposing you could have infinite energy, or you could accelerate arbitrarily fast or whatever. Those aren't necessarily visualizable, but they're are they thought experiments?
Yeah, that's an excellent question. I would think so, and this is the reason why we are not committing to this mental image account, because we think that in those situations, so if you have a contrafactual situation that is not necessarily imaginable or nicely constructed as this one, that contrafactual situation might be enough to allow you to reveal some inconsistencies. So you might consider that as a thought experiment, even if you cannot imagine that necessarily. This is the reason why we are also suggesting an alternative view that doesn't rely on this imagination part or this image that represents or mirrors necessarily some realistic situation. So I agree. And this is why I also answered to you that I presented this as two separate things, thought experiments and mathematical derivations, because as it was, Hawking derivation actually gave some support to the resolution of this thought experiment. So in that case, you might be able to distinguish them, but I know that there's no sharp line, and that's some of the thought experiments are much more complicated, and they are on the border of being just a mathematical derivation, and they need each other. So I agree with all of that. And I definitely think that you don't necessarily need this imagination, but this imagined scene scenario in order to have the experiment.
Yeah, I wanted to ask, thank you for this talk, it was very nice. So there's many scientists I'm a theoretical physicist. There's many scientists in other disciplines that frequently tell me and colleagues, and also in a blog that I'm sending every other day, basically, that what I do, which is basically this, math and thought experiments, is not science. So can I take what you are saying to me?
Please, that's the idea.
Okay, because I think, I fully agree about the conclusive knowledge.
Wonderful.
So can I cite you to these people and say?
Of course, and the paper is published, so you can you can actually do it. Yeah. No, great that you agree. So that was actually some of the motivations to come here, because we do want to say something that is in line with what you do, right? And yeah, so we are much beyond Popperian ages, so we are much more open-minded now as philosophers of science, and we're welcoming different alternative methods of confirmation or of doing science as well.
So the, what's it called, the scientific cycle, or no, what's it called?
The top,
No, the cycle that science should be, no, the scientific method.
the scientific method, yeah, the hypothetical deductive method. We're beyond the hypothetical deductive. Happy that you agree with that.
Ramesh, I think there was a hand back, so if I missed it, please raise your hand.
Yeah, so, it's a nice procedure and distinction that you laid out. So the step 5 is where the thought experiment produced a clear conflict and, revealed that there's an inconsistency. Sure, everybody can agree that there's an inconsistency. And then there's the resolution business, right? The resolution, your second example in particular, showed that there were 2 conjectures, each trying to resolve this inconsistency. And for each of them, somebody could come along with another thought experiment, essentially. Like, the Bekenstein bound, the complaint was, instead of a cubical box, I use some other box, I need some other bound or whatever, right? So there was a clear counter thought experiment that could show that it doesn't work. So therefore it remains a conjecture. And so was the, Wald and Unruh stuff where somebody showed. But if I now imagine a scenario in which there are, let us say, half a dozen conjectures, and every one of them you can come up with a counterexample which shows that it doesn't work, and therefore is not the final answer. But if one of them survives every onslaught, right? Nobody can come up with a way to show that it doesn't work. At that point, does that become the truth, or do we still say, no, it's only a conjecture, just that nobody has been smart enough to disprove it? But
It could become a
I don't know, what do you think?
I think if it stands the test of time and all the onslaughts of the many smart people, then I think it's the truth until somebody disproves it.
Okay.
Yeah, but do you guys have a thought on that, or are
We
these
do have many
always
thoughts.
going to be conjectures?
We have many thoughts. Yeah, I think I am. Yeah, it could be a little bit more demanding there, but we can say that the resolution is very robust, and that's reason enough to trust the resolution.
Okay.
But I wouldn't go beyond to say that's the truth. So I would stop a little bit before that, but I would not think that it's absurd that people continue doing that if we don't have anything else to support that resolution. I think if a resolution is robust enough and it's the only game in town,
Yes.
let's say, that means that it makes sense that you should maybe trust that resolution. Then the question is how much you trust it. So if you believe that it's true, fine. I would not go that far, but I would say we have reason to trust it.
It wasn't basically Ryan saying that we should maybe think twice before accepting things like third law as a
Yeah, right. We could say the third law was the truth.
Yeah, that's
before.
right.
Would you say the third law was the truth before it was disproved?
Yeah, that's what I mean.
Yeah, exactly.
Or like black hole stability. I mean, which
Yeah.
I think is an assumption that everyone's making here all the time, and I support it, but it's kind of nice that people are trying to actually prove it.
Yeah, I think still, if you have more evidence or more tools, even if they are not empirical evidence, because it's hard to be that demanding with black hole thermodynamics. But if you have other types of evidence that go in that direction that support your resolution, I think that's better. And that's what happened with Bekenstein resolution. So that at some point that was the only game in town. But when Hawking derived the temperature, that was extra support because that was an independent way of arriving at the same result. And I think if you have that, then it's better. You have more. So I'm going to be Bayesian today. And the more evidence you have coming from different places, the more reasons you have to trust your theory. That's how I would put it.
So this current status is that the Garrosh paradox is still a paradox. There are multiple conjectures, but every one of them has got a counterexample. Is that correct?
To my understanding, there's no consensus. Yeah, you might.
That's
think-
crazy.
Yeah, yeah.
Can you do that in ADS or that? You know,
That's another, there's another, yeah.
Right.
Yeah.
There's a question in the Zoom chat.
Yes, Shep, please.
Yeah, can you hear me?
Yeah.
Yeah, it's a very interesting talk. Sorry, I have to watch this remotely. But I just wanted to question the relationship between thought experiments and real experiments, because there seems to be this trend, of course, that what was once a thought experiment purely can become a real experiment. If you'd asked Einstein, about light bending and things like that, he wouldn't have imagined like the EHT, I think, or the photon rings, things like that. So what in your view is the relationship evolutionarily between thought experiments and real experiments? At some level, do thought experiments have to turn into real experiments? Or what happens when they do? And how can thought experiments guide real experiments if we think expansively about what could happen in the future?
Yeah, thank you. Thank you. That's a very interesting question. I think it depends on the type of thought experiments. As you say, at some time we didn't, some of the Einstein's thought experiments we didn't see becoming real experiments, and some were done, or even Maxwell demon, right? There have been computer simulations that are more real, let's say, than the thought experiment suggested by Maxwell. But I think depends maybe whether a thought experiment can become a real experiment depends on how realistic the thought experiment is in order to be able to perform it in a real laboratory. But the interesting question is whether you will learn more by performing a real experiment instead of the thought experiment. I think from what I said that for the resolution part, it would make sense to turn some of the thought experiments into real experiments, because you can have more sort of robust, more convincing evidence of the resolution if you perform a real experiment. But for the revelation of the inconsistency part, you wouldn't gain that much by turning a thought experiment into a real experiment. Because what I believe is that a thought experiment is just enough to expose attention between different theories. So I think the motivation to turn a thought experiment into a real experiment has to do with the resolution part, with the way of solving this tension between the different statements, normally statements coming from different theories.
Okay, thanks a lot.
Thank you.
I have a, if I'm nice. So I have a question about how you're seeing the different proposals for thought experiments in relation to each other and in relation to your proposal. Namely, I thought at first I would be pro a kind of pluralistic stance of, in some cases, the Norton view does make sense. Maybe it's closer to a mathematical derivation. In some cases, a mental model does make sense. But then I thought maybe actually some of these fit into various steps of your proposal, like step 2 could be a Norton style thing.
Yes.
So maybe you can say a bit more about how I should approach them.
Excellent. So thank you. So first of all, I am not committed to the thesis that all thought experiments have the main functions of reveal and resolve inconsistency. All the thought experiments that I have investigated do, but I don't want to go that far and say that all of them have only this function of revealing and resolving inconsistency. I'm open to the possibility that thought experiments are used for other purposes, even pedagogical purposes. You might build a thought experiment in your mind that is related to physics just to teach some material to students. So I don't want to say that the only function of thought experiments is to reveal and resolve inconsistency to all thought experiments. But for these thought experiments, that is the principal function. And as you said, when I said that you unfold the scenario, so you apply theoretical statements into the scenario, the contrafactual scenario that you are suggesting, I think most of the time you can interpret that as an argument. So this is where my view is also compatible with Norton's view. And in the cases in which you can imagine this, that might also be a mental representation of a thought experiment. But as I was replying to Peter, I don't think that you always need to have a mental image in order to have a thought experiment. So if you have it, then my view will also be compatible with this mental image approach, because sometimes that's what you do. You represent a situation, you approximately represent a situation in your mind. But sometimes you might have a thought experiment that is not representable in that way. And with respect to vocalish, we are very close. I also think that the main role of these thought experiments is to teach us about non-empirical virtues of our theories. That is the consistency, the revelation of an inconsistency, and also the possibility of resolving this inconsistency. But she speaks about different virtues, and we stress in particular this revelation of an inconsistency and the resolution of that inconsistency. So this is more or less how this relates to the other views that are defended in the literature.
Okay, if there are no other questions, join me in thanking Patricia.
Thank you. Very nice.
Okay, yeah.